So far, we've looked at a few basic examples of what happens when we have an infinite collection or an unlimited collection of numbers, either a sequence of numbers or a series or sum of numbers. And what we're trying to do is make a definition that captures all of these situations. First of all, we'll look at the limit of a sequence of numbers. And so the core idea is that if we have a sequence of numbers, an, and we want to ask, is there some number that ultimately that sequence is getting closer to, and we'll call it L, by taking enough numbers in the sequence, n, what we've got to show is that the difference between our limit L and any number in the sequence is smaller than some very small number epsilon. Okay, let's try and understand that visually. Say we've got the sequence of numbers 1 over n, where n is a positive integer. Okay, where you start is the tolerance, how close we want our number to be to our limit, and we call that epsilon, which is a Greek form of e. And here in the graph, we're plotting the values of 1 over n as n, the positive integer, gets larger and larger, so 1 over n gets smaller. If we make epsilon smaller, epsilon is how far away we're going to accept our number in the sequence from the limit, which we believe to be 0. So as we make it smaller, that region around our limit is getting tighter and tighter, and it's only the numbers after n equals 7 fall within that boundary around our limit. And what's important is that it's not just the first number n equals 7 in the sequence, but all of the numbers after that lie within this tight boundary around our limit L equals 0. Now this assumes that we know what the limit is. We'll come on to what we do when we don't know the limit. Now as we make that boundary tighter or smaller, then that strip is going to get narrower, and the number of terms we need to get to and beyond increases. But ultimately we will find a number n so that all subsequent numbers in the sequence are closer than our boundary, our epsilon, around our limit. The really basic idea is we can select a boundary around our limit. First of all, that's the first thing we take. And that can be as small as we like, but cannot be 0. And then what we have to show is that there is some point in the sequence where the difference between our limit and the current value of our sequence is less than our boundary. But in addition, all subsequent numbers in our sequence also lie within that boundary. And more than that, that remains true no matter how small epsilon is, how close it gets to 0. Let's have a look at it for the sequence 1 over n squared. Again, if we make epsilon smaller and smaller, and we accept that our limit is 0, then that region, that strip around our limit, is getting tighter. And again, we can show that no matter how small epsilon is, but still bigger than 0, that there is some value of n, some positive number, for which all subsequent values of 1 over n squared lie within that strip or boundary around our limit. Our final example is minus 1 to the n over n. And if we plot that graph, we see the values are oscillating because of the minus 1, but they're getting closer to the limit L equals 0. If we make our epsilon smaller, our strip or boundary gets tighter, but there is some value for every value of epsilon bigger than 0, for which all subsequent numbers in the sequence will lie within our strip. Now, if we want to convert that idea into formal mathematics, we get this rather intimidating expression. But what it's trying to say, and the definition of each term is given down here, is that if we say that a sequence of numbers an has some value called a limit, and that's true as we take more and more terms, that is the same as saying for any epsilon, which is generally a small number but is bigger than 0, there's going to be some positive whole number such that all numbers bigger than that will mean the difference between any value in the sequence later than our value n, its difference between the value in the sequence and our limit is going to be less than our chosen epsilon. So all numbers, all differences between our number in the sequence and our limit is going to lie within the strip after some value n. So we start with that epsilon, we show that there is some positive integer so that all later numbers in our sequence lie closer to the limit than our chosen tolerance epsilon. After you've read through that and tried to understand it, think about and answer the questions. Does the limit have to be reached? And what happens if epsilon is halved? And a common mistake is the sequence equals its limit eventually. Come up with what you think is the correct answer to those, then click on them to see the given answer.